Okay, example 2, it says a square sheet of card of side 12 centimeters has equal squares of side x removed from each corner, and the edges are then turned up to make an open box of volume V. Show that the volume of the open box is given by this equation. So the difference in this question is you now have to set up the equation which connects the subject variable and the other variable. So we're going to have to draw a diagram here because it mentions a square sheet of card and then mentions a box. So if we take a look then at our solution for part A, we start with a square sheet of card and we're told each side of the square is 12 centimeters. We're then told that at each corner of this square there are little squares cut away. So I'm going to draw squares of side x. So identical squares of side x are then removed from each corner of the sheet. Now, what happens once these little square corners are cut out? Then all the long edges are folded inwards. So this long edge is folded in, the opposite edge is folded in, and likewise for the top edge and the bottom edge. They're all folded in, and the end result is going to be an open box, an open cuboid. Now our job is to get an expression for the volume of this cuboid. So we're going to have to get an expression for this side, and then obviously the height. So this side here is exactly the same as this length here. Now to get this length, we're taking the original length, which was 12, we're subtracting an x and another x, so overall that's going to be 12 minus 2x, that side. And put it in brackets, because there's more than one term. Likewise, this side on our cuboid, on our box, is this side when it's folded in. Okay, so this side is found by starting with 12, taking away an x, and then taking away another x. So it's also going to be 12 minus 2x. The height of the box is actually the length of one of the squares that was cut out, because bear in mind when you fold one of these sides in, this little bit here is going to become the height. So the height of the box is just x. So now we can get an expression for the volume of the cuboid. So volume of box, so that's length times breadth times height, and then chuck in the expressions. So we've got 12 minus 2x multiplied by another 12 minus 2x, then multiplied by x. So the plan then, we're going to multiply these two brackets together and then multiply the result by x. So I'm going to put brackets around the pair of brackets to do those first. So that's going to give us 144 minus 24x minus another 24x is minus 48x, and then plus 4x squared. And then the result is being multiplied by x. So tidy that up. That's going to give us 4x cubed. Just putting the powers in order, starting with the largest and going downwards. X times minus 48x is minus 48x squared. And then x multiplied by 144 is plus 144x. Okay, as required. So v equals 4x cubed minus 48x squared plus 144x as required. Part A. Okay, so part B then, it says find the value of x which makes the volume a maximum. So the subject variable is a maximum or a minimum when the first derivative is equal to 0. So in other words, when dv by dx equals 0. So that means we're going to be differentiating. So let's differentiate this first. So part B, let's get dv by dx. So dv by dx is going to give us 12x squared. Differentiate the next term, we're going to get minus 96x. And then differentiate the final term, plus 144. Okay, so volume, or V, is a max or min when the first derivative equals 0. Okay, so we'll set our first derivative equal to 0, so 12x squared minus 96x plus 144 equals 0. Divide through by 12. And then we're going to solve the quadratic by factorizing, and we'll do that by using product and sum. So two numbers here are going to be minus 6 and minus 2. And then we do the usual. So we've got a product of two brackets equals 0. So the first one could be 0, which means x equals 6. Or the second bracket could be 0, which means x equals 2. So what we've done is we've actually got two critical values here. The reason there are two critical values is because one of them will make v a maximum and the other one will make v a minimum. Now we're looking for the value that makes v a maximum. So we have two critical values for the other variable. Okay, so we have to now prove that v is a maximum. So we're going to prove that v is a max stroke min. That means we need the second derivative. So we need d2v by dx squared. So we're going to differentiate dy by dx, sorry, dv by dx, so there's dv by dx, differentiate that again, so d2v by dx squared, so that is going to give us 24x, and then minus 96. Okay, so the plan now is we're going to chuck each of these critical values into the second derivative to see which one makes the second derivative less than 0. Because if the second derivative is less than 0, then that's telling you the subject variable is going to be a maximum. So, we'll start with x equals 2. So the second derivative, d2v by dx squared. So that's going to be 24 times 2 minus 96. So that's going to give us 48 subtract 96, which is minus 48 which is less than 0, so that's telling you in that case v is a maximum. So that must mean when we chuck in x is 6, the other critical value, then v will be a minimum. So let's check it. So when x equals 6, second derivative d2v by dx squared. So it's going to be 24 times 6, subtract 96. So that's going to be 144 minus 96 is going to give us positive 48. That's bigger than 0. So that's telling us then that v is a minimum in that case. Okay, so we've now answered the question. We've worked out the critical value of the other variable, which makes the subject variable a maximum. So answer, subject variable v is a maximum when x equals 2 centimeters. And that's going to be our answer then for part B. Okay, part C. So part C says find the maximum volume. So we've already worked out the critical value of x that makes the volume a maximum. So all we do now is sub that value of x into the volume equation to get the maximum volume. So maximum volume we're going to chuck in the critical value that makes it a maximum, which remember is 2. So when x equals 2, we're going to get v equals 4 times 2 cubed minus 48 times 2 squared plus 144 times 2. And again, we can tidy that up. So we're going to have 2 cubed is 8. And then we're multiplying that by 4, that's going to be 32. And then we're subtracting 48 times 4. And then we're adding on 144 times 2. And that's going to give us 128. And because it's a volume, it's obviously going to be centimeters cubed. So that is the maximum volume for the critical value of the other variable being 2. If we did sub in the other critical value for the other variable 6, we would get the minimum volume, so it would obviously be some value less than that.